All right, so now we're going to talk about the ideas of work and energy. So we looked at kinematics, right? The physics of an object in motion with a constant acceleration. And we looked at forces, right? What happens to an object whenever we apply a force to cause acceleration. But whenever we were looking at forces, we were looking at snapshots in time. We weren't looking at what happens to this object throughout the motion of the object, right? These were just snapshots. So let's say we have this person and they are pushing a block and this block moves forward. So change in position and we have a force applied. Well, whenever we consider a force applied over some distance, we call this work. So technically, the definition of work is equal to the force dotted into the change in position of this object. But in an algebra-based physics, we define work as the force parallel to the direction of motion times the change in position, right? So in this situation, our force is applied fully in the direction of motion, so work would be equal to the force applied times this change in the position of the object. So this is our definition of work. And work has units of newtons times meters. So work is just telling us that a force is being applied and it is causing an object to move some distance. So why do we want the parallel component only? Well, if we consider a block sitting on a surface, and let's say there is a tension force applied, and this block moves in the positive x direction, right? We need to break our force down into the x and y components. Well, if this block is only moving in the x direction, the y component of that tension is not contributing anything to the forward motion of this object. So the work is the force parallel or on the same plane as the direction of motion of this object. So in our case, it would be the x component of the tension force times the displacement of the object, or our work would be equal to tension cosine theta, change in position. So we only want the component of the force that is on the same plane of motion as the object's displacement. So what if we have an object that has multiple forces acting on it, right? A great example of this would be a block on an inclined plane. Let's say the object is moving up the inclined plane. There is tension, but there is also some sort of kinetic frictional force. Well, we have two forces that are on the same plane as the motion of the object, right? We have the tension that is going positive in the same direction as the motion of the object, and we have the frictional force that is going in the opposite direction of the motion of this object. So the total work done is going to be the summation of forces that are parallel times this change in position. So I can actually break this up into two separate calculations. I can figure out the work done by the tension, which is going to be equal to the tension force that's parallel to my change in motion. And I can have the work done by the frictional force, and this is going to be the kinetic frictional force, parallel, times my change in position. So let's say the vector for my tension force is -7 newtons, negative because it is pointing in the negative direction. The vector for the kinetic friction is 2 newtons, positive because it's in the positive direction. And my displacement is going to be negative, for simplicity, 1 meter. And it's negative because it's pointing in the negative x direction. So what would be the work done here? Well, the work done by the tension force is going to be -7 newtons times -1 meters. And this is going to be +7 Newton meters. Now, it's interesting because our work is going to be a scalar value. It's not apparent through the algebraic approach to this, but a dot product gives us a scalar. So work is a scalar value. And you'll see that we have a positive 7 Newton meters, right? Our work is a positive value. That's because this tension is doing positive work, right? This tension is really what's causing the motion of this object. It's doing positive work. Now, what about the frictional force, right? My friction was 2 newtons times -1 meters. And so my frictional force is giving me a -2 Newton meters. My work done by the frictional force is a negative value, right? It's kind of resisting the motion. So it's doing negative work. So work can be a positive or a negative value, but it is always going to be a scalar. So once we have a definition of work, we can define something called power, right? So power is just our rate at which work is done. So power is going to be work divided by some change in time. Now what's interesting here, right, is our work had force and displacement, and now our power involves time. So we can now consider the motion of an object with changes in position as well as changes in time and have force relating to that. So this means that power is equal to our force parallel times our change in position divided by our change in time. Power now can relate force and velocity to each other. So this relationship between forces, displacement, velocity, power is going to connect these forces that we've been talking about to something called energy. And we can do that through the work-energy theorem. So this work-energy theorem tells us that work is equal to something called our change in kinetic energy. So let's assume that we have this person and they are pushing a block. The force applied is totally in the positive x direction, and the displacement is in the positive x direction. So I'm going to calculate my work as equal to the force parallel times my change in position. And my force, in this situation, mass times acceleration, right? Newton's second law. So work is equal to mass times acceleration times some change in position. So this acceleration times a change in position can be connected to our kinematics equations. I think it's important to note that this is presented in a general physics class like it's an obvious connection, but somebody spent their life like creating these connections, and we are learning hundreds of years of science in a couple weeks, right? So if this connection isn't obvious to you, or if you thought to yourself, well, I would have never figured that out, don't worry, somebody spent their life doing this stuff. So we have this kinematic equation, right? The final velocity squared is equal to our initial velocity squared plus 2a delta r. Well, look, I have acceleration times a change in position. I have acceleration times a change in position. So I can use this to connect work to the velocity of the object. So rearranging this kinematic equation, I get velocity final squared minus velocity initial squared divided by 2. So my work is equal to mass times this final velocity squared minus the final initial velocity squared divided by 2. So I'm going to expand this out. Work is equal to 1/2 mv final squared minus 1/2 mv initial squared. And this 1/2 mv squared is what we call kinetic energy. So kinetic energy is going to be the energy of motion, right? If something has a velocity, it has a kinetic energy. It has energy of motion. So our work is equal to this change in kinetic energy. So all moving objects have kinetic energy. The faster an object moves, the more kinetic energy that this object has. Well, what about other forces, right? If there's something special about Newton's second law and work, there has to be something else for other forces, right? So what about gravity? So let's say that we have an object and it is dropped from rest. The only force acting on this object is the force of gravity. So let's figure out the work done here. Well, the work is equal to the force parallel times my change in position. For simplicity, my change in position is just going to be delta y, our change in our y location, right? So this is y initial, this is y final. I'm going to have y final equal to 0, ground level. And my force here is going to be the force of gravity. It has a negative direction to it. And all of this gravitational force is acting in the same direction as my displacement of my object. So work is equal to negative mg delta y. Now I'm going to break this out, right? So work is equal to negative mg y final minus negative mg y initial. So this mgy is going to be our potential energy, right? This is going to be energy associated with the positions of an object relative to another object. So why is this positive mgy? Well, potential energy is a scalar value, and this negative is associated with directionality. But I can state that my work is equal to negative potential energy final minus negative potential energy initial. This tells me that my work is equal to negative change in potential energy. And this is for work that is done by gravity. So potential energy is actually a property of a system, not an object. Kinetic energy is the property of an object because an object has velocity, but an object doesn't have a location, an mgy, right? We need a location unless this location is relative to something else. So whenever we're thinking about like this ball sitting on top of like a cliff, its position is relative to, in this situation, ground level, right? That y value only has meaning whenever it's relative to something else. So potential energy is a property of a system, not an object. And if it's a property of a system, that means that potential energy can have different values depending on how we choose to define our coordinate system. So this is a great example of that. Let's say that I have a person standing on the ground and they're holding a ball up in the air at 5 meters above ground level. And they are going to drop this ball into a well. And the well is negative 15 meters deep. Well, in this situation, I can calculate my potential energy initial is going to be mgy initial. Let's, again, for simplicity, assume that the mass is 1. My potential energy in this initial condition is going to be 1 times 9.81 times 5, and I get 49.05 joules. The units for energy are joules. So what about whenever this ball hits the bottom of the well? So let's call that my final position. So my potential energy final is mgy final, meaning that my potential energy final would be negative 147.15. So what is my total change in potential energy? Well, my total change in potential energy is going to be 147.15, 49.05, 196.2 joules, right? Joules. So potential energy is all about positions, and we get to pick our y values based on where we have placed our coordinate system. So I can do this all over again with my coordinate system at a different location. right? This is ground, but now I am going to have y is equal to 0 at the very bottom of the well, and this means that my person's ball is going to be at y is equal to 20. So doing this calculation all over again, my potential energy initial in this situation is going to be 20 times 9.81, 196.2 joules, and my potential energy final is 0. Why? Because my y is equal to 0 is final. I still have the same change in potential energy. It's still 196.2 joules as my change in, these are negative values, negative 196 because it lost potential energy. It fell. So my location specific potential energy changes, but the total change in potential energy is the same throughout this entire process. So potential energy represents the potential for an object to move, right? So I personally don't like having a negative potential energy at a specific location because this implies that it has negative potential to move. I would rather have my final position have 0 potential energy because, like, if I think about this, like, this ball is not going to fall any further. It has 0 potential to fall any further at the bottom of this well. Having a negative potential energy, I don't really prefer that, but both of these are correct. So the change in potential energy is the same in both of these setups. It's just the location-specific potential energies are different. So that tells us that the only thing that really means something is the change in potential energy, not the location-specific potential energy. So what about other forces? Well, we're going to introduce a new force here, and this is spring force or elastic force, and this is Hooke's law. So this equation, F is equal to negative kx, is Hooke's law, and k is going to be our spring constant. It is a property of the spring. So you'll notice that this is a negative force, right? It is negative because it is a restoring force. It is restoring an object back to equilibrium. So our equilibrium position is going to be when a spring is relaxed and at rest. If we stretch the spring out, we will have a positive x value. If we compress the spring, we will have a negative x value. And this is interesting because it tells us, right, that if we have a negative x value, our force is going to be positive, right? It's going to want to push this object in the positive direction. And that makes sense because if I compress a spring, it's going to want to push back towards its equilibrium. If I have a positive x value, my force is going to be a negative value. And that makes sense because if I stretch the spring out, it's going to want to pull back towards its equilibrium. It's going to want to pull back in the negative direction. So if we have a new force, we probably also have work done by that force. So work, again, force parallel times our change in position. Well, work done by a spring force is a little bit more complex. That's because this force is variable, right? It changes with the displacement of the object, right? So the further I pull a spring out, the stronger that force is going to be. The more I compress that spring, the stronger the force is going to be. And so we can't really do this algebraically for variable forces. So our definition of work, for those of you in the class who have had calculus, work is equal to F dot dr. We can find work by integrating from 0 to x. Our force is negative kx. We are going to replace the r with an x. So this gives us that work is equal to negative 1/2 kx squared. And if we recall, work is equal to a negative change in potential energy, this means that the potential energy of a spring is 1/2 kx squared. So at this point in time, you're probably thinking to yourself, why are we doing a bunch of mathematical derivations? Well, that's because this is the physics. The physics is finding mathematical representations for physical phenomenon. So elastic or spring potential energy, this potential energy 1/2 kx squared is energy that is stored in a spring whenever it is compressed or stretched. It's still a stored form of energy. It has the potential to cause motion. So the further that the spring is from equilibrium in the positive or negative direction because of this square, the greater the potential energy it has. So there are other forms of potential energy, right? We have electrostatics, things like this, but forces that have potential energies associated with them are something called conservative forces. So not every force has a potential energy associated with it. So, for example, there's no such thing as frictional potential energy. And that's because whenever friction does work, it is converting energy into a form that is not easily recoverable. It turns it into thermal energy. And we'll talk about thermal energy much later in the semester.